Have you ever thought that the universe also had a long night before dawn appeared? After the Big Bang, before the first stars were born, the universe sank into a dark age, silent and cold, as if it were waiting to be awakened. In that vast emptiness, what was quietly taking place? Did darkness plant the seeds of light, or nearly swallow everything that could exist? Leave a comment with your thoughts. And next, we will return to the beginning of the universe, where this story truly begins. What if the most famous explosion in history was never an explosion at all, but the quiet unfolding of space itself, like a breath that suddenly became a universe? That single shift in perspective changes everything. Because when people imagine the Big Bang, they often picture fireworks inside a pre-existing void. Yet the deeper idea is stranger and more beautiful. It is not that matter flew outward through space. It is that space began to stretch, carrying matter and light along with it, like raisins drifting apart as the dough rises. In that sense, the Big Bang is less a bomb and more a beginning of distances, a birth of between. And if between was born, then time was born too. Not as a clock hanging outside the universe, but as a feature of the universe's own growth. There is a line often attributed to Stephen Hawking that captures the mood of this idea, that asking what came before the Big Bang may be like asking what lies north of the North Pole. Whether you take it as metaphor or literal caution, it points to a hard truth that is also strangely comforting. Our ordinary questions were forged inside time, so we must be gentle when we use them near time's horizon. Still, we can follow the trail of evidence, and it leads to a picture that feels almost meditative in its precision. In the earliest moments, the universe was not a place filled with things. It was a condition, a state, a searing intensity, where the idea of separate objects barely makes sense. Energy and matter were deeply entangled in a hot, dense sea. Temperatures were so extreme that familiar structures could not hold. Protons and neutrons were not yet the stable building blocks we know. Atoms were not yet possible. Light, which we treat as the great messenger across space, did not travel freely. It was trapped in a churning, opaque fog. To picture this without losing yourself in equations, imagine standing inside a blizzard so thick that a flashlight beam becomes a glowing smear a few inches from your face. The light is real, but it cannot cross the storm. It keeps colliding with snowflakes, again and again, scattered in every direction, unable to form a clear path. The early universe was like that, except the snowflakes were charged particles. Photons tried to stream forward, but they kept crashing into free electrons and bouncing away. The cosmos was brilliant and yet blind, luminous and yet sealed. This is what people mean by a primordial plasma. Not plasma like a neon sign in a tube, but a state where atoms cannot survive because the heat tears them apart. Electrons roam freely, and nuclei cannot keep their companions. In such a world, light does not behave like a traveler. It behaves like a restless thought in a crowded room, constantly interrupted, never finishing a sentence. And that is why the earliest universe, even if filled with radiation, was effectively a hidden universe. Then, as expansion continued, cooling came like a long exhale. Eventually, the temperature fell enough for electrons to settle into orbit around nuclei, forming the first neutral atoms. When that happened, the blizzard thinned. The universe became transparent. Light, after being held close for so long, finally slipped free and began the journey that, billions of years later, would reach our instruments as the cosmic microwave background, the afterglow of a young cosmos. In a way, it is the oldest light we can see, a soft echo of that first release. But the story does not begin there, because something even more mysterious seems to have happened far earlier, on a timescale so tiny that it strains language. Cosmologists call it inflation, a period when the universe expanded not just steadily, but explosively fast, as if space itself briefly pressed the accelerator to the floor. If the Big Bang is the opening chapter, inflation is the sudden widening of the page, the moment the stage grows vast enough for a long drama to unfold. One of inflation's most important roles is almost poetic. It smooths the universe, ironing out wild wrinkles, making distant regions look surprisingly similar. Yet it also leaves behind faint ripples, delicate imperfections that will later become everything we recognize. Here, a simple image can help again. Imagine a perfectly calm lake at dawn. From a distance, it looks like a mirror, flat and uniform. But if you kneel close, you notice tiny shivers on the surface, created by a breeze you cannot see. Those small ripples matter, because they decide where reflections break, where patterns form, where drifting leaves collect. In the early universe, the lake was the distribution of energy and matter. Inflation smoothed it, but microscopic fluctuations remained, and gravity would eventually amplify them. The universe did not build its structure from perfect order. It built it from faint irregularities, as if the cosmos needed a whisper of asymmetry to create a symphony. This is where quantum fluctuations enter the story, and they sound like abstraction until you realize what they imply. At the smallest scales, nature does not sit still. Even empty space is restless with uncertainty. Tiny variations appear, not because someone designed them, but because the quantum world does not allow absolute stillness. Inflation then stretches those tiny variations to cosmic size, turning quantum murmurs into the seeds of galaxies. It is one of the most astonishing bridges in all of science. The behavior of the infinitesimal becomes the architecture of the immense. There is a phrase associated with cosmologist Alan Guth that often captures inflation's spirit, that inflation is the ultimate free lunch. The wording is playful, but the idea is profound. In a universe governed by relativity and quantum fields, the growth of space can take something extremely small and make it unimaginably large, while leaving behind just enough structure to explain why galaxies exist at all. If that sounds like magic, it is only because our everyday intuition was not built for the early universe. The equations, however, point to a cosmos whose most creative act may have been expansion itself. And when we ask how space, time, matter, and energy appear together, we are really asking how a single description splits into many faces. In modern physics, matter and energy are not strangers. They are two expressions of one deeper accounting. Heat becomes particles. Particles annihilate into light. Fields vibrate and take on identities. As the universe cools, symmetries break, like a perfectly balanced tone separating into harmonies. Different forces that may have been unified at unimaginable energies begin to behave differently. The universe gains texture. It becomes less like a pure note and more like music. In the first fractions of a second, it is not helpful to imagine planets or atoms. It is more honest to imagine conditions. A pressure so extreme that even the concept of a stable thing is temporary. A density so high that distance is not yet an everyday idea. A heat so intense that identity itself is fluid. And yet, out of this, the universe moves toward clarity. Cooling allows building blocks to survive. Survival allows complexity. Complexity allows stars. Stars allow heavy elements. Heavy elements allow chemistry. Chemistry allows oceans. And somewhere in oceans, a kind of matter learns to look up and wonder what the beginning was. When you hold the whole chain in your mind, the educational value is not just in knowing the terms, but in seeing the continuity. There is no sharp border where mystery stops and knowledge begins. There is a gradient, like twilight. At the bright end, we have the cosmic microwave background, a measurable relic. Farther back, we have strong models supported by many lines of evidence. Earlier still, we have powerful ideas like inflation, which match observations in key ways, while still inviting deeper tests. And near the very beginning, we reach questions that may require new physics, new ways of thinking, new instruments, and perhaps new humility. Yet humility here is not surrender. It is a kind of respect. The universe is not obligated to fit our instincts. It is only obligated to be itself. And the more we learn, the more the beginning feels less like a dramatic blast and more like a delicate opening, a moment when the rules of distance and time switch on, when light is born into a crowd, when tiny quantum trembles are promoted into the blueprint of galaxies. So when you hear Big Bang, you can gently replace the image of a bomb with the image of expansion. When you hear primordial plasma, you can picture a blizzard of charged particles that keeps light close. Not because the universe is dark, but because it is too crowded to be seen through. When you hear inflation, you can imagine a calm lake stretched to the size of a cosmos, carrying tiny ripples outward until they become the first hints of structure. And when you hear quantum fluctuations, you can remember that the grandest patterns in the sky may have started as the smallest uncertainties nature allows. In the next part, we will follow what happens after that first transparency, when the universe, having released its ancient light, still enters a long, quiet chapter and then slowly kindles the first stars, the first galaxies, and the first true dawn that ends the cosmic night. What if the oldest photograph of the universe is not a picture of stars at all, but a soft, ancient glow, drifting toward us from a time when everything we now love about the night sky did not yet exist? If you could step into that first light, you would not see galaxies or constellations. You would see a universe still learning how to become transparent. In the beginning, the cosmos was not a place you could look through. It was a thick, brilliant fog, so hot and dense that light could not travel freely, and matter could not settle into calm forms. In that early furnace, the universe did something both simple and miraculous. It started building the first ingredients of everything we would later call home. This is where primordial nucleosynthesis enters like a quiet composer writing the opening bars of a symphony. In the first few minutes after the Big Bang, as expansion cooled the fire just enough, protons and neutrons began to stick together. Not into planets or atoms yet, but into the first atomic nuclei, the bare hearts of future atoms. The result was a universe that emerged from its initial chaos with a surprisingly clean recipe. Mostly hydrogen, a generous portion of helium, and only a whisper of lithium. No carbon for life. No oxygen for oceans. No iron for blood. Just the lightest building blocks, like a painter preparing only 3 colors before the canvas has even been stretched. The question people often ask is why the universe did not simply keep forging heavier and heavier elements right then, as if it had endless time and endless patience. But the early universe was rushing, expanding so fast that it was always slipping out of its own grasp. To make heavier nuclei, you need the right balance of heat, density, and time. In those first minutes, the temperature was dropping rapidly, and the density was thinning like steam rising from boiling water. Fusion could happen, but only briefly, and only in the simplest steps. Hydrogen formed easily because it is the simplest nucleus, just a single proton. Helium formed because the universe still had enough heat and crowding to let small nuclei collide and stick. Lithium tried to appear too, but the conditions were already changing. And lithium is fragile in that early environment, easily broken apart, easily prevented from accumulating. So the universe moved on, leaving behind a chemical signature that still echoes in the measured abundances we observe today. There is a deep elegance in this limitation. It means the universe did not begin with the richness of a finished world. It began with the bare minimum, and it saved complexity for later chapters. As the astronomer Carl Sagan famously reminded us, "We are made of star stuff." That sentence carries a hidden timeline inside it, because it implies that the heavier elements in our bodies were not present at the start. They had to be cooked later, inside stars, through long lifetimes and violent deaths. The early universe gave us the raw clay, but the kiln would come much later. And yet, even this simple chemistry did not immediately give us a clear sky. For hundreds of thousands of years after those first minutes, the universe remained a bright plasma, a sea of charged particles. Electrons moved freely, and photons, the particles of light, kept colliding with them again and again. Light was everywhere, but it could not travel far, like headlights in dense fog, illuminating the mist but never cutting through it. The universe was luminous, but not transparent. Then came recombination, one of the most quietly dramatic moments in cosmic history. As expansion continued, the temperature finally fell to a point where electrons could settle down and bind to protons, forming neutral hydrogen atoms. This was not a single instant like a switch being flipped, but a transition, a cooling into clarity, and the consequence was profound. Once electrons were mostly locked into atoms, photons stopped scattering so constantly. For the first time, light could move freely across space. The universe became transparent, not because it created light, but because it stopped trapping it. It is one of the most beautiful inversions in all of physics. The first light we can still see today was released not by a new explosion, but by a new calm. To picture recombination without getting lost in equations, imagine a crowded ballroom where everyone is dancing wildly, bumping into one another, spinning so fast that you cannot walk across the room. Photons in the early plasma were like a person trying to cross that ballroom, constantly jostled, constantly redirected, never able to move in a straight line. Recombination is the moment the music slows and the dancers pair off, forming steady couples, leaving open paths across the floor. Suddenly, you can walk. Suddenly, you can see. The room did not become brighter. It became clearer. That is why recombination matters so much. The light released at that moment is what we now call the cosmic microwave background, the CMB. It is not light from stars. It is not the glow of galaxies. It is the afterglow of the early universe itself, stretched and cooled by billions of years of expansion until it now arrives as microwaves. When we detect it, we are not just looking far away in space. We are looking back in time to an era when the universe was young enough to still carry the memory of its own birth in the texture of light. Calling the CMB the first photograph of the universe is not poetic exaggeration. It is almost literal truth. It is the oldest light that can reach us, the earliest image that is not blocked by the plasma fog that came before. And like any photograph, it contains information in its grain. The CMB is astonishingly uniform, but not perfectly so. It carries tiny variations in temperature, tiny ripples, like faint freckles on an otherwise smooth face. Those minute differences are not imperfections to be ignored. They are the seeds of everything. They are the places where matter was slightly denser, where gravity would later pull harder, where clouds would gather, where stars would ignite, where galaxies would assemble. As Stephen Hawking once put it, we are just an advanced breed of monkeys on a minor planet of a very average star. But we can understand the universe. In the CMB, that understanding begins in earnest, because those faint ripples are the earliest map of future structure. Here is another image to make it tangible. Think of the CMB like the surface of a pond just after a stone has been tossed in. From far away, the pond looks calm. Up close, you see gentle rings spreading outward. The universe at recombination was similar. On the largest scales it was smooth, but it held subtle waves of difference that would later grow into the vast cosmic web. The CMB is not a random glow. It is a record of initial conditions, a quiet confession of how order begins. But then comes the question that feels almost heartbreaking. If recombination released the first light, why did the universe fall into darkness afterward, instead of becoming a bright kingdom of stars? The answer is simple in concept and immense in implication. The CMB was not a lamp that stayed lit. It was a flash that kept traveling. Those photons, once freed, streamed outward in every direction, thinning as the universe expanded, cooling as their wavelength stretched. Meanwhile, the matter left behind was mostly neutral gas, hydrogen and helium, spread out and cold. There were no stars yet because stars require patience. They require gravity to gather gas into dense knots. They require clouds to collapse and heat up. They require time for the first structures to assemble. So after the CMB, the universe entered a long twilight, what we call the cosmic dark ages, not because nothing existed, but because nothing was shining yet in a sustained way. This is where the story becomes almost meditative, because the universe teaches us that light does not arrive just because the conditions are possible. It arrives when the conditions become inevitable. After the first flash, matter had to learn how to clump. Gravity had to work slowly, drawing slightly denser regions into deeper wells, building halos, gathering gas, compressing it until the first star could finally ignite. Darkness, in this sense, was not failure. It was incubation, a quiet interval where the universe assembled the stage before raising the curtain. And there is a subtle educational gift hidden in this sequence. The early universe is not a tale of instant complexity. It is a tale of thresholds. A threshold where nuclei could form. A threshold where atoms could form. A threshold where light could travel. A threshold where gravity could sculpt. Each step is a kind of cosmic permission slip, allowing the next chapter to exist. Hydrogen and helium were not a lack. They were a beginning. Recombination was not just chemistry. It was a clearing of the sky. The CMB was not just radiation. It was memory made visible. And now, with that memory in our hands, we can feel the next question rising naturally, like a breath before speech. If the universe became transparent and then went dark, what finally broke the silence? What gathered the first clouds? What lit the first star? What turned a cooling fog into a sky with depth and fire? That is where we go next. From the first ingredients and the first light, we step into the long night that followed, and we begin tracing the slow, gravity-driven path toward the first dawn of stars, where the universe does not merely remember its beginning. It begins, for the first time, to shine. What if the most important chapter in cosmic history happened when there were no stars to witness it? Not a single galaxy shining. Not a single sunrise anywhere. Only a universe that had already been born, yet had not learned how to glow. After the Big Bang's first fierce heat faded, the cosmos entered what we call the Dark Age. Not dark because nothing existed, but because light had no easy path to travel. For a long stretch of time, the universe was filled with a thin, expanding sea of hydrogen and helium, cooling quietly as space itself stretched wider. This era begins after the first atoms formed, and the primordial light was released as the cosmic microwave background, and it ends when the first stars finally ignite. In most standard pictures, that means the darkness lasted for hundreds of millions of years. Roughly from the moment the CMB was set free about 380,000 years after the Big Bang, until the first starlight began to appear tens to a few hundreds of millions of years later. If that sounds like emptiness, it helps to remember what the darkness really was. It was not a void. It was a presence. A gentle, invisible ocean of neutral gas, threaded with gravity, and accompanied by an ancient afterglow we can still detect today. The CMB is often described as the universe's first baby picture, because it is the earliest light that can travel freely to us. And yet, after that radiant release, the cosmos did not immediately become a fireworks show. Instead, it dimmed, like embers settling after a blaze, leaving behind a hush so deep it can feel almost spiritual to imagine. Here is where the mystery becomes educational in the most beautiful way. Because the Dark Age is not a pause in the story. It is the part where the plot quietly turns. The universe, in that long night, was not doing nothing. It was preparing conditions for structure. It was letting gravity do its slow, patient work. The key actors are the tiny density ripples left behind from the earliest moments. Minute differences in how matter was distributed. A little more here, a little less there. Those slight unevennesses were the seeds. They were the reason the universe could ever become interesting. They were also the reason anything like here and us could eventually exist. Stephen Hawking once captured the heart of this idea with a line that still feels like poetry in a lab notebook. We are the product of quantum fluctuations in the very early universe. And Carl Sagan, in his own calm, luminous way, gave us the human consequence. We are made of star stuff. Placed gently into this story, these quotes are not decoration. They are a bridge between the mathematics of the early cosmos and the intimacy of our own existence. But how do those ancient ripples matter during a time with no stars and no galaxies? Imagine a perfectly still lake at dawn. If the surface is truly smooth, no currents gather, no patterns rise, no wave ever becomes a wave. Now imagine that same lake with the faintest tremble, barely visible, like the touch of a breeze. Those tiny disturbances are enough for motion to organize, for currents to form, for complexity to begin. In the Dark Age, the universe was that lake. The ripples were those leftover density fluctuations. Gravity slowly amplified them, pulling more matter into slightly denser regions until the first clumps began to form. Not bright yet, not dramatic yet, but real. The earliest scaffolding of everything we will later call cosmic architecture. A second image can bring it even closer. Think of bread dough rising. If the dough were mixed with absolute perfection and no tiny bubbles, it would bake into something dense and uniform, with no airiness, no texture, no life. But real dough has small pockets, slight variations, tiny imperfections that let it expand in intricate ways. The early universe was similar. Its imperfections were not mistakes. They were the breathing spaces where structure could grow. Now consider the question that sounds simple, but is actually profound. If the universe had been completely uniform, what would have happened? The answer is almost startling in its plainness. Nothing much. No stars would have formed because there would be no slightly denser regions to collapse first. No galaxies would have gathered, no planets would have cooled, no chemistry would have diversified beyond the simplest ingredients. A perfectly smooth universe would be a quiet universe forever, like a song with no notes changing. And in that stillness, there would be no observers asking questions. So our existence depends on those early imperfections, in a way that is both scientific and deeply moving. We often associate imperfection with failure, but the cosmos teaches the opposite. A universe that is too perfect is sterile. A universe that is slightly uneven is fertile. Those tiny initial differences, so small they can be described as fluctuations, became the first invitations for gravity to build. And gravity, given time, always builds. This is why the CMB matters so much in the story. Because it is not only a relic glow, it is a map of the early universe's subtle unevenness. It carries the fingerprints of those density ripples in its faint temperature variations. When we study the CMB, we are not just admiring an ancient light. We are reading the earliest evidence that the universe was never perfectly smooth. And that not perfectly smooth is the reason the cosmos could become a home. From that point, the Dark Age becomes less like a void and more like a gestation. The universe is cooling, expanding, and quietly gathering itself. Neutral hydrogen fills the space between forming structures, and the first clumps deepen. Eventually, in the densest pockets, gas collapses far enough, heats enough, compresses enough for nuclear fusion to begin. And when that happens, darkness breaks. Not everywhere at once, but in scattered places first, like the first candles lit across an endless plain. If you listen closely to what this teaches, it is not a sensational lesson. It is a calm one. We do not need the universe to rush. We need it to have the right conditions, and the patience to let them mature. The Dark Age reminds us that absence of light is not absence of activity, and it reminds us that small beginnings can be powerful beyond imagination. So when you ask how long the cosmic Dark Age lasted, you are really asking how long the universe needed to become capable of making light again. When you ask whether it was empty, you are learning to distinguish darkness from nothingness. And when you ask about the role of tiny density ripples, you are touching one of the most essential truths in cosmology, that the grandest structures arise from the smallest differences. And perhaps the quietest question beneath all of this is the one that stays with you after the facts settle. If the universe had been perfectly uniform, nothing would ever have changed enough for you to be here. So in a very real sense, your existence is written into the earliest faint unevenness of reality itself. A gentle asymmetry in the beginning, carried forward through billions of years, until it became eyes that can look back and wonder, what if the first stars were born not from fireworks, but from silence? A silence so deep that even light had to wait for gravity to finish its slow sentence. In the early universe, there were no planets, no oceans, no carbon in any living breath. Only hydrogen and helium, spread like a thin, cooling mist after the Big Bang, drifting through an expanding darkness. Before any star could ignite, the universe had to become transparent enough for history to be seen at all. That is why the story begins with a strange milestone. The moment electrons finally settled down and joined protons to form neutral atoms. When that happened, photons that had been trapped in the hot plasma were suddenly set free, and they began their long journey through space. We still receive them today as the cosmic microwave background, a faint afterglow that is less like a spotlight and more like an ancient whisper. Not an image of stars, but an image of conditions. A gentle map of tiny density ripples, the first hints that almost the same everywhere was never truly the case. Those ripples mattered more than any dramatic explosion. Because if the early universe had been perfectly smooth, nothing would ever have gathered. Nothing would ever have lit up. A star is, at its core, a victory of clumping over spreading. And clumping begins when gravity patiently tips the balance, even when it seems too weak to do anything at all. Why does the weakest force become the deciding one? Because gravity never gets tired. Electromagnetism can cancel itself out when positive and negative charges balance. Nuclear forces act only across subatomic distances, but gravity is always attractive, always reaching, always adding. One atom of hydrogen pulls on another with a force so small it feels like a joke. Yet given enough time and enough atoms, the joke becomes architecture. Gravity is the quiet rule that turns a fog into a lighthouse. As the universe cooled after the CMB was released, hydrogen and helium filled space like a cold ocean. Within that ocean, the faint ripples in density began to grow under their own pull. Regions that were slightly denser drew in more gas, becoming denser still, like a slow whirlpool gathering leaves. And here, one of the simplest truths in nature appears. When gas falls inward, it heats up. Compression is a kind of friction with existence. The deeper the collapse, the hotter the core. Eventually, in the heart of a dense cloud, temperature and pressure rise until nuclei can finally fuse. A star is born not when gas exists, but when gas becomes a furnace. To picture it, imagine a winter valley where air is perfectly still. A faint dip in the landscape collects colder, heavier air, and over time the fog thickens there while surrounding regions remain clear. Nothing explodes into formation, yet the valley becomes its own weather system. In the early universe, the valley was a small gravitational advantage, and the weather was a cloud collapsing toward ignition. But these first stars were unlike most stars we see today. They were what astronomers call population 3, the earliest generation, formed from nearly pure primordial gas, hydrogen and helium, with almost no heavier elements. That detail changes everything. In modern star-forming clouds, heavier elements help the gas cool by radiating energy away, allowing it to fragment into many smaller clumps. In the beginning, the gas had far fewer ways to cool. It stayed warmer, resisted breaking into small pieces, and so it tended to collapse into fewer, larger objects. The first stars in many models were giants, some tens, perhaps hundreds of solar masses. They burned bright not because they were lucky, but because they were massive enough to crush their cores into furious fusion. There is a line often attributed to the astrophysicist Carl Sagan, "We are made of star stuff." It is famous because it is both poetic and strictly physical. And it becomes even more astonishing when you realize that in the earliest times, there was no star stuff yet to speak of. The universe had to manufacture its own complexity, one generation at a time. Massive stars live fast. Their enormous gravity raises core temperatures so high that nuclear reactions run at a relentless pace. They shine like bonfires in a dark field, but they burn through their fuel quickly. Where a star like our Sun can glow for about 10 billion years, a supermassive primordial star may last only a few million years. Cosmically speaking, that is a sigh, and their deaths are not gentle. Some end as titanic supernovae, scattering newly forged elements into space. Others may collapse more directly, falling inward until even light cannot escape, leaving behind black holes that could become the seeds of later monsters at galactic centers. To make this feel real, think of a candle versus a flare. A candle is steady and patient, designed for longevity. A flare is blinding and brief, designed for impact. Population 3 stars were flares written in gravity. They did not exist to last. They existed to transform. So where did the first heavy elements come from? Not from the Big Bang itself, which produced mostly hydrogen and helium, with a touch of lithium. The heavier elements carbon, oxygen, silicon, iron were forged in stellar cores and in the violent furnaces of stellar death. Inside a massive star, fusion builds elements like a ladder, step by step, until iron appears. But iron is a kind of dead end. Fusing iron costs energy instead of releasing it. And when the core reaches that point, it can no longer support itself. Collapse follows, and collapse can trigger an explosion powerful enough to seed the surrounding universe with the materials for rocks, oceans, and biology. Here, another famous voice fits naturally. As the astrophysicist Subramanian Chandrasekhar once wrote, "The stars are the laboratories of the universe, because in them, nature performs chemistry at temperatures and pressures we cannot recreate on Earth." The first laboratories were crude, violent, and brilliant. Yet without them, the universe would remain chemically simple. And simplicity would mean no continents, no iron in blood, no oxygen to breathe. And this is why people say we are the descendants of the first stars. Not in a symbolic sense alone, but in a direct material lineage. The calcium in your bones, the oxygen in your lungs, the iron that lets your blood carry life. None of it came from the Big Bang. It came from stellar interiors and stellar funerals. We are not visitors in a foreign cosmos. We are one of its late forms, shaped by earlier light. A second example can make this even clearer. Imagine trying to build a city using only 2 types of bricks. You could make walls, but not windows, not wiring, not the varied materials that make life comfortable and complex. The early universe had only hydrogen and helium, 2 bricks that could not build biology. The first stars were the factories that invented new building materials, then dispersed them across space so later generations could assemble planets and, eventually, living minds. So when we look back toward the cosmic microwave background, we are not just looking at an old photograph. We are looking at the stage before the actors arrived. The CMB is the universe's first clear breath after the fog lifts, and within its tiny ripples lie the reasons stars could form at all. From that quiet pattern, gravity began its long work. From that work, the first stars ignited. From their brief lives, the first heavy elements were born. And from those elements, everything familiar worlds, water, cells, stories became possible. If you let that sink in, the universe starts to feel less like a place and more like a process. A slow awakening in which darkness is not the enemy of light but its cradle. And perhaps the most calming thought of all is this: the cosmos did not rush to create us. It simply followed its deepest tendencies: clump, heat, shine, transform. Yet in doing so, it produced a creature capable of asking how the first stars began, and why they had to die for us to be here. So as we move forward, hold that question gently. When the first light rose, it was not only the universe becoming visible. It was the universe beginning the long path toward understanding itself. Have you ever wondered how the universe escaped its own darkness without anyone there to strike a match? To answer that, we have to shrink ourselves down to the smallest stage where the drama begins, the atom. Because ionization sounds like a grand cosmic word, but at the atomic level it is simply separation. An atom of hydrogen is a quiet duet, one proton holding one electron in a shared embrace. When enough energy arrives, that bond breaks, the electron is freed, and the atom becomes charged, no longer neutral. That single change, repeated across oceans of gas, is the difference between a universe that hides its light and a universe that lets it travel. Now imagine the first stars switching on in a universe that was still filled with neutral hydrogen. Those early stars were not gentle candles like the sun, but fierce blue furnaces, pouring out ultraviolet photons with the sharpness to pry electrons loose. Neutral hydrogen is especially sensitive to this kind of light, because it only takes a photon above a certain energy to knock the electron free. So the first starlight did not merely illuminate space, it altered the nature of space's most abundant substance. It was light acting like a sculptor, changing the material it touched. Here is a simple picture you can hold in your mind as the physics unfolds. Think of hydrogen as a tiny ballroom pair, the proton leading, the electron following. A hard ultraviolet photon arrives like a sudden clap of thunder between them, and the partners separate. That is ionization, not mystical, not abstract, just energy changing a relationship. And once separated, those free electrons begin to interact with radiation and fields in a new way, turning ordinary gas into an electrically active medium. At this point, it is tempting to say, wasn't the early universe already a plasma right after the Big Bang? Yes, and that question matters, because it's where many people blur two very different chapters into one. The primordial plasma after the Big Bang was everywhere at once, thick, hot, and so crowded with charged particles that light could not travel freely. Photons kept scattering off free electrons like headlights trapped in dense fog, unable to go far in any direction. But the plasma of the cosmic dawn was different in spirit and in geometry, because it did not begin as an all-encompassing sea. It began locally, around sources of light, like islands forming in a dark ocean. And here we touch the heart of reionization. Reionization is the long transition in which the universe's neutral hydrogen was stripped back into charged particles again, not by the original heat of creation, but by the later radiation of stars, galaxies, and perhaps the earliest feeding black holes. It is the universe's second electrification, powered by starlight rather than by the initial fireball. If the first plasma was the universe too hot to be transparent, reionization is the universe becoming transparent again by changing what blocks the light. To see why it starts in patches, picture a winter lake freezing. It does not freeze instantly everywhere with identical thickness. It begins along the edges, in sheltered bays, around conditions that favor the change, then spreads until the surface becomes continuous. In the same way, reionization began where the first stars and galaxies formed, in denser regions that could collapse earlier under gravity. Their ultraviolet light carved out bubbles of ionized gas around them, and those bubbles expanded with time. Some regions stayed neutral longer, like pockets of night refusing to let go. That is why the universe during this era can be described as looking like soap foam. Not because it was literally bubbles you could pop with a finger, but because the structure was a patchwork of expanding ionized regions separated by neutral hydrogen. Each luminous source inflated its own cavity of charged gas, and as more sources ignited, the cavities grew, touched, and merged. If you could float above it in impossible silence, you would see a cosmic landscape of glowing cavities and darker walls, a three-dimensional lace of light and shadow. The bubbles were the footprints of the first persistent light. Here is a second everyday example to make the transparent part feel real. Think of a foggy street where your car headlights only illuminate a few meters ahead. That is like a universe filled with neutral hydrogen that absorbs and scatters certain photons quickly. Now imagine the fog thinning until the beam reaches far down the road. That is what reionization accomplishes on the largest scale, not by moving the light faster, but by changing the medium so the light can pass. This story also connects beautifully to the earlier, quieter relic that still surrounds us: the cosmic microwave background. Before any stars existed, there was a moment when the universe cooled enough for electrons to settle back onto protons, creating neutral hydrogen for the first time. When that happened, the relentless scattering stopped, and light finally streamed outward, almost unhindered. That released glow is what we now observe as the CMB, the ancient afterglow that carries the imprint of the universe when it was still young. George Smoot once said, "If you're religious, it's like looking at God." Whether you take that literally or poetically, the point is clear. The CMB is a direct message from a time when the cosmos first became transparent, long before the first stars rekindled ionization. And that brings us to the timeline question. When did the universe become transparent to starlight in the way we mean today? After the first stars began to appear, roughly a few 100 million years after the Big Bang, their bubbles of ionization grew for hundreds of millions of years. By around 1 billion years after the Big Bang, the process was largely complete, and the intergalactic medium became mostly ionized, allowing ultraviolet and visible light to travel vastly farther through space. This is not a single switch flipped in an instant, but a dawn that spreads, a slow brightening where the last pockets of neutrality finally give way. If you step back and let the meaning settle, reionization is not merely a technical phase on a timeline. It is the universe learning to be seen. The first transparency gave us the CMB, a baby picture of a cosmos without stars. The second transparency, driven by the first stellar fires, opened the deep distance so that light from early galaxies could cross billions of light years and reach us. Carl Sagan's line, "We are made of star stuff," lands differently here, because the same early stars that forged the first heavy elements also changed the very clarity of space, making a universe where observation, memory, and astronomy could exist at all. So when you picture that soap foam universe, remember what it really represents. It is not chaos. It is the first architecture of illumination. It is the cosmos practicing sunrise, bubble by bubble, until the night becomes a medium that no longer holds light captive. And when we study it, we are not only studying distant physics, we are tracing the moment the universe became readable, and therefore, in a profound sense, knowable. Have you ever wondered who, or what, flipped the universe from a foggy night into a clear morning? Long before galaxies looked like islands of light, space was filled with a thin, simple soup, mostly hydrogen and helium, cooling as it expanded. For a while, the universe was so hot and crowded with charged particles that light could not travel freely. Then, as it cooled, electrons finally settled onto protons, and neutral atoms formed, releasing photons that could at last stream across space. As John C. Mather famously said, "The cosmic microwave background is a baby picture of the universe. That baby picture, the CMB, is not a starry photograph, but a glowing afterimage of a time when the cosmos first became transparent." And yet, after that first release of light, the universe did not stay bright. It dimmed into a long, quiet stretch we call the Dark Ages, where neutral hydrogen drifted through vast distances like mist over an unlit sea. Here is where the central mystery begins to breathe. Neutral hydrogen is very good at swallowing energetic ultraviolet light, the very kind of light needed to tear electrons away and make the gas ionized again. So the question is simple to ask, but hard to answer. What produced enough power, for long enough, across enough volume, to reionize almost everything we can see today? The first suspects are the legendary population 3 stars. They were not like the sun we know. They formed in a universe with no metals, no carbon or oxygen to help gas cool efficiently. So the first clouds tended to collapse into fewer, heavier stars. Bigger stars burn hotter, pour out more ultraviolet radiation, and live fast. sometimes ending in fierce explosions or direct collapse into black holes. In that sense, population 3 stars look like perfect candidates for reionization, because reionization is, at heart, a story about ultraviolet photons escaping into intergalactic space. But there is a catch that keeps scientists cautious. These stars were likely rare, short-lived, and difficult for their light to escape, because newborn stars form inside dense gas that eagerly absorbs radiation. To picture this, imagine trying to light an entire city using a handful of enormous fireworks set off inside thick fog. Each burst is dazzling, but much of the light is immediately swallowed close to where it was born. If population 3 stars were the fireworks, the question becomes whether there were enough of them, spread widely enough, and whether their ultraviolet could leak out of their birth clouds efficiently enough to change the whole sky. The universe does not reionize from brilliance alone. It reionizes from brilliance that escapes. That brings us naturally to the next suspects, the primordial galaxies. A single giant star is intense, but a galaxy is a choir, and even a rough, early choir can sing loudly if it has enough voices. Young galaxies could host many massive stars at once, producing a steady flood of ultraviolet photons. As these galaxies multiplied, their ionized regions would grow like clearings in a forest of mist, expanding and eventually merging until the mist was mostly gone. This is why many researchers lean toward early galaxies as the main drivers. Not because one galaxy is unstoppable, but because there can be so many of them, working together across time. A second example makes this easier to feel. Think of neutral hydrogen as a layer of frost coating a window. A single warm breath creates a small, clear patch, but it refreezes if the warmth is brief. Now imagine thousands of small candles placed behind the glass. Each candle melts a tiny circle, and as more candles appear, the circles expand, touch, and join, until the window becomes mostly clear. That is the logic of galaxies during reionization. Many modest sources can outperform a few extreme ones, simply by persistence and numbers. And then come the darker engines, the early black holes and quasars. A quasar is a black hole feeding, turning in falling matter into fierce radiation. Unlike starlight, quasar light can reach higher energies, including X-rays, which travel farther and can heat gas over large distances. If abundant early quasars existed, they could have helped carve wide corridors through the neutral hydrogen. But the puzzle tightens again. We do see quasars very early in cosmic history, which is itself astonishing, because it means some black holes grew enormous very quickly. Yet it is not clear that there were enough quasars everywhere, early enough, to dominate reionization alone. So, is reionization the triumph of population 3 stars, or the collective work of early galaxies, or the far-reaching influence of quasars? The most honest answer today is that it likely involved all three, braided together in a way that depends on time and place. Perhaps the first sparks came from massive primordial stars, briefly punching holes in the fog. Then galaxies took over, multiplying and sustaining the ionizing background. Meanwhile, black holes and quasars may have added heat and reach, smoothing and extending the process in regions where starlight struggled. If that sounds like a satisfying synthesis, you might ask why science cannot simply confirm it and move on. The reason is that reionization is not a single event with one timestamp. It is a shifting patchwork across the sky, a process that unfolds over hundreds of millions of years, with different neighborhoods lighting up at different times. We infer it through delicate clues. The way distant galaxies fade at certain wavelengths, the shadows of hydrogen in quasar spectra, the polarization imprinted on the CMB, and the promise of future maps from the faint 21-centimeter signal of neutral hydrogen. Each clue is powerful, but each also has uncertainties, and the universe does not hand over its early chapters in clean, printed pages. There is also a deeper difficulty that is almost philosophical, yet entirely practical. We are trying to measure the escape of light from the first structures through a medium that keeps changing while the sources themselves evolve rapidly. Small assumptions can ripple into big differences. How clumpy was the primordial gas? How efficiently did early stars form? How porous were young galaxies to ultraviolet radiation? How common were feeding black holes? And how much of what we see is starlight versus the glow of energetic accretion? Still, this uncertainty is not a weakness of science. It is the honest shape of the frontier. The CMB gives us the universe's childhood portrait, serene and smooth. Reionization, by contrast, is the adolescence, messy and dramatic, when the first lights learn to travel, and the cosmos learned to become visible in the way we experience it now. As Carl Sagan said, "We are made of star stuff." Reionization is part of how that star stuff earned the right to be seen, how the universe turned on the conditions for complex chemistry to spread, and for later generations of stars, planets, and life to emerge. And if you listen closely, you can almost sense the story behind the equations. A universe that cooled into silence, then gathered itself into the first flames. A dawn built not by a single lamp, but by countless small sources finding ways to shine through. In the next part, we will return to that earliest beginning, the primordial matter and the CMB, because to understand who reionized the cosmos, we must first understand the moment the universe became transparent, and why it ever fell into darkness at all. What if the first cities of starlight were built on invisible foundations we can never touch, yet cannot live without? In the beginning, the universe was a hot, simple ocean, where matter and light were tangled so tightly that nothing like a galaxy could breathe. Then came the moment when atoms finally formed and photons slipped free, spreading into space as the cosmic microwave background, a quiet afterglow that still washes over us today. In that ancient light, there are tiny wrinkles, faint temperature variations, like the soft imprint of a fingertip on glass. Those wrinkles are not decoration, they are destiny, because they mark where gravity had something to hold on to. As Vera Rubin famously said, "There is more to the universe than meets the eye." That sentence feels almost like poetry. Yet it is also a map, because the visible universe is only the foam on a much deeper sea. Dark matter does not shine, does not cool by emitting light, does not form atoms the way ordinary matter does. Yet it outweighs the luminous cosmos and quietly shapes its architecture. If the cosmic microwave background is the baby picture of the universe, dark matter is the hidden skeleton already inside that infant, guiding how it will grow. The first dark matter halos appear as the universe expands and cools, when those tiny early imbalances begin to amplify under gravity. Imagine a landscape where the slightest dips deepen over time, not because the ground moves, but because gravity patiently pulls more material into the same places again and again. Dark matter clumps first, because it can start collapsing without being slowed down by pressure from radiation and hot gas. It forms halos, gravitational bowls, long before there is any starlight to announce them. Ordinary gas, the hydrogen and helium left from the early universe, is like mist drifting across that landscape until it finds the bowls and begins to gather. Here is one way to picture it without equations. Think of dark matter as the scaffolding around a building that has not been constructed yet. The scaffolding is not the home. You will never live in it. But without it, the bricks have nowhere to rise, no shape to follow, no corners to become real. That is why dark matter's role in galaxy formation is less like adding mass and more like making places, creating gravitational addresses where gas can settle and start the long work of becoming stars. When the first galaxies finally ignite, they are small not because the universe lacked ambition, but because it was young and the raw materials were still learning how to behave. The gas is nearly pristine, poor in heavy elements, and that matters because heavy elements help gas cool and fragment. Cooling is the art of letting gravity win, and in the early universe cooling is hard, so the first bursts of star formation can be intense and abrupt, like a match striking in thin air. These early galaxies are also tiny because their halos are small. and small halos have shallow gravity wells, meaning everything they build can be easily disturbed. That is why the first galaxies are so violent. They form stars rapidly, and those stars are often massive, short-lived, and impatient. Soon they explode as supernovae, flooding their surroundings with energy and shock waves, heating the gas and throwing much of it outward. The galaxy, still a fragile newborn, can be partly evacuated by its own brilliance. But gravity does not stop caring just because a blast happened, so gas cools again, drifts back in, and the cycle begins anew. Starbirth, supernova, collapse, return, again. A second example can make this feel more tangible. Picture a campfire in a calm valley. The fire warms the air so strongly that it pushes smoke and heat outward, thinning the immediate surroundings. Yet when the flames quiet down, the cool night air flows back into the same hollow, because valleys collect what the wind cannot hold. Early galaxies behave like that valley, except the valley is a dark matter halo and the returning air is primordial gas. This loop of eruption and return is one reason the first galaxies can look chaotic, irregular, and fiercely alive. Now add time, and add neighbors. In the early universe, distance is smaller in the sense that everything is closer together in an expanding fabric, and halos are constantly finding one another. Collisions and mergers are not rare accidents, they are a common language. Two small galaxies meet, their gas clouds compress, star formation flares, and their dark matter halos interweave like two invisible storms passing through each other. Over and over, these encounters build larger systems, and over they rearrange the shapes, spinning up disks, puffing up spheroids, feeding central black holes, and stirring the gas into new rounds of creation. Fritz Zwicky once warned of a surprising result, that most of the mass is unseen. The surprise deepens here, because the unseen is also the organizer, the quiet choreographer of a cosmic dance. What looks like chaos up close becomes structure from far away. Because when countless halos grow and merge, gravity does not paint randomly, it draws lines. Matter streams along preferred paths, flowing into filaments, gathering at intersections, leaving behind vast, darker voids. This is how the cosmic web emerges, not as a pattern imposed from outside, but as the natural handwriting of gravity on an expanding universe. Dark matter forms the broad strokes, long filaments and dense nodes. Ordinary matter follows, cooling, shining, and turning those nodes into galaxies and clusters, like lanterns hung on an invisible net. If you could drift outside the universe and look back, you would not see a smooth fog. You would see a tapestry, and each bright thread would trace an unseen chord beneath it. And if you return to that first afterglow, the cosmic microwave background, its faint wrinkles begin to feel like whispers that became roads. The early universe did not need to be loud to be purposeful. It only needed slight differences, enough for gravity to start gathering, enough for dark matter halos to appear, enough for gas to find a home, enough for the first small, fierce galaxies to burn, break, and rebuild. From that repeated rhythm, the universe learns its shapes. From that invisible foundation, the visible sky is born. Have you ever wondered why the oldest light in the universe reaches us not as bright starlight, but as a deep, stretched whisper in the infrared? When we look far away, we are not just looking across distance. We are looking back in time, into an era when the cosmos was still learning how to shine. In the beginning, the universe was not a sky full of stars. It was a hot, dense sea where matter and light were tangled together, like fog so thick that even a beam could not travel a step without being scattered. Then the universe expanded and cooled, and a quiet turning point arrived. Electrons finally settled onto protons to form neutral hydrogen. In that moment, light was set free to travel long distances for the first time. And what escaped became the cosmic microwave background, the CMB, a fossil glow that still surrounds us today. It is not merely an image. It is a memory of the universe at the instant it became transparent. a soft afterglow that tells us what the primordial ingredients looked like before stars began to cook the heavier elements. But even after that first release of light, the universe entered a long hush. No stars yet, no galaxies yet, only vast fields of hydrogen and helium, drifting in the dark, with tiny unevennesses in density left behind as the seeds of everything to come. And this is where the story of redshift begins to matter, because the universe does not simply sit still while light travels. Space itself stretches. So, as ancient photons cross billions of light years, the fabric they ride upon expands beneath them, pulling their wavelengths longer, like a melody slowed, until every note becomes deeper and more drawn out. That is why the earliest light from the first galaxies is shifted toward the infrared. It is not that those galaxies were only red. It is that the universe has lengthened their light during the journey, turning what was once ultraviolet and visible into something softer, cooler, and harder to catch. Redshift is the ruler we use for this stretching. It measures how much the wavelength of light has been expanded on the way to us, and therefore how far back in cosmic history we are peering. The larger the redshift, the more the universe has grown since that light began its trip, and the younger the universe was when it was emitted. If you want an image that makes it intuitive, imagine a dot painted on a balloon. As the balloon inflates, every point moves away from every other point, and any wave drawn on its surface would be stretched along with it. Light crossing an expanding universe experiences something like that same gentle, relentless pull. This also explains why ordinary optical telescopes struggle to see the cosmic dawn. Optical instruments are built to collect the wavelengths our eyes evolved to notice. Visible light. But the universe's first great sunrise does not arrive in those colors anymore. By the time it reaches us, its blue and gold have been pulled into infrared shades, beyond what optical telescopes can properly capture. And there is another veil as well. Between us and those earliest sources lies a sea of gas that can absorb and scatter certain wavelengths. And in the very early universe, that sea was richer in neutral hydrogen, making the path even more challenging. So the cosmic dawn is not simply faint. It is shifted, filtered, and partially hidden by the very medium that once filled all of space. This is why the James Webb Space Telescope feels like a doorway rather than just a new camera. Webb was built to listen to the universe in infrared, to catch photons that have been traveling since the first structures were forming, and to do it with a mirror large enough and detectors sensitive enough to register that ancient, weakened signal. It is not that Webb changed reality. It changed what reality we can access. As Nobel laureate George Smoot once put it, the cosmic microwave background radiation is the Rosetta Stone of cosmology. Webb is one of the tools that helps us read the next lines that follow that stone, tracing how the smooth early universe grew texture, structure, and finally, light. And Webb's power is not only in making distant smudges visible, it is in breaking their light apart. Spectroscopy is the reason a faint patch becomes a story with dates, chemistry, and motion. When you spread a galaxy's light into a spectrum, you reveal a barcode of absorption and emission features, signatures left by elements like hydrogen, oxygen, and carbon. Those signatures shift with the redshift as well, sliding to longer wavelengths in a predictable way, which allows astronomers to measure distance and cosmic age more precisely. At the same time, the relative strength and pattern of features hint at what kinds of stars are present, how enriched the gas is, and whether energetic processes like accreting black holes might be contributing to the glow. Edwin Hubble captured the spirit of this approach in a line that still guides modern astronomy. Equipped with his 5 senses, man explores the universe around him and calls the adventure science. Spectroscopy is one of those senses refined into an instrument, letting us taste the chemical history of a galaxy we can never touch. To make spectroscopy feel less abstract, picture sunlight passing through a glass prism, becoming a rainbow. Now imagine that rainbow with thin, dark lines carved into it. Those lines are fingerprints. Specific atoms absorb specific colors. When we see the same pattern in the light of a distant galaxy, shifted toward red, It is as if the universe is telling us, in a coded voice, what it is made of and how long the message has traveled. Yet light is only one messenger. There is another signal, quieter and in some ways even more revealing, the 21-centimeter line of neutral hydrogen. This radio wavelength is produced by a subtle change in the hydrogen atom, and it can trace the presence of hydrogen gas through the dark ages and into the era of reionization. If the CMB is the universe's baby photo, then the 21-centimeter signal is closer to an ultrasound of the cosmic dawn, showing where the gas is still neutral, where it is warming, and where the first sources are carving ionized bubbles into the primordial fog. A second example may help. Imagine a vast winter field at night. You cannot see the ground well, but you can sense temperature patterns with an infrared camera. Now replace that field with hydrogen filling space, and replace the camera with radio measurements that track hydrogen's faint signature. What you begin to map is not just objects, but the changing state of the medium between them, the stage on which the first stars performed. This is where the square-kilometer array, the SKA, becomes pivotal. Because the 21-centimeter signal is extraordinarily faint, and because Earth is loud in radio noise, you need a collecting area and sensitivity on a scale we have never had before, plus careful techniques to separate the cosmic whisper from the foreground roar of our own galaxy and technology. The SKA is designed to do exactly that, to survey the sky with a reach deep enough to reconstruct the timeline of reionization and to test whether our models of early structure formation match what the universe actually did. In a sense, Webb gives us portraits of early galaxies, while SK aims to give us the landscape they were born into. And when you connect these pieces back to the primordial matter and the CMB, the narrative becomes almost meditative in its coherence. The CMB tells us the early conditions, the density ripples, the composition, the temperature map of a universe just becoming transparent. Those ripples then grow under gravity, gathering hydrogen into the first halos, lighting the first stars, and beginning the transformation of a neutral cosmos into an ionized one. Redshift is how we keep time in this story. Infrared is where the oldest starlight has drifted. Spectroscopy is how we read the chemical letters inside that light. The 21-centimeter line is how we track the invisible hydrogen ocean that once filled everything. Webb opens the infrared window, and SKA listens to the hydrogen itself. Taken together, they do not just answer a technical question about why light turns red. They help us understand how a simple universe became a complex one, how the first atoms gave way to the first stars, and how the darkness that followed the CMB was not empty at all, but quietly preparing the conditions for every galaxy, every planet, and every observer who would one day look back and ask these questions. So, as we continue, keep one gentle idea close. The cosmic dawn is not only the first time the universe lit a lamp, it is the moment the universe began to write in light, and today, with new eyes and new ears, we are finally learning how to read its earliest sentences. What if the earliest galaxies were not supposed to exist at all, at least not in the way we are seeing them? What if the universe, still in its infancy, was already building cities of light, while our equations insist it should have been learning to crawl? When astronomers first began to sift through the deepest images, the surprise was not that there were galaxies so far away. The surprise was their confidence. They looked too bright, too massive, too assembled, like finding a fully grown forest in what should have been bare volcanic rock. As Carl Sagan once reminded us, we are a way for the cosmos to know itself. And in moments like this, you can feel that sentence turn around and look back at us, as if the cosmos is asking whether we truly know what we thought we knew. The simplest version of the puzzle goes like this. In the standard story, the universe begins hot and dense, then expands and cools. Matter is almost smooth, with only tiny ripples in density. Gravity patiently amplifies those ripples, gathering gas into dark matter halos, lighting the first stars, and slowly, over time, building galaxies. Yet some of the galaxies we now see at very high redshift appear startlingly luminous, suggesting a large amount of starlight packed into a very short cosmic window. The question is not merely, how did they get there? But, how did they get there so quickly, and shine so loudly, and still fit inside the rules we trust? Before we rush to rewrite the universe, it helps to remember what too big can mean. Brightness is not mass. Light can be inflated by feverish star formation, by bursts of hot young stars, by dust that reshapes what escapes, or by an active black hole feeding at the center, turning in falling matter into a lighthouse. If you have ever tried to judge the size of a distant city at night, you know how easy it is to confuse brightness for scale. A small city during a festival can look larger than a sprawling metropolis under a blackout. In the same way, a compact galaxy undergoing an extreme starburst can masquerade as something far heavier, simply because it is burning through its fuel at a breathtaking rate. Still, even after we account for these tricks of light, the tension remains. How could galaxies assemble so fast when the universe was young, when time itself had barely given gravity room to work? Here, the invisible scaffolding becomes central. Dark matter is the quiet architect in our models, carving gravitational wells that allow gas to gather. If those wells formed earlier or were more efficient at pulling in gas, then structure could bloom faster than we expected. Not because the universe cheated, but because we underestimated how quickly it can take advantage of a tiny imbalance. There is a humility in that thought, because it reminds us that the cosmos does not need to be dramatic to be surprising. It only needs to be precise. And the gas, the ordinary matter, may not have behaved as simply as our neat summaries suggest. Primordial gas was not like the familiar clouds we picture today. It was metal, poor, chemically young, with different cooling pathways, different feedback, different fragility. If early stars formed with a different typical mass, if stellar populations were skewed toward brighter, shorter-lived giants, then a galaxy could appear brilliantly mature while still being physically young. Imagine walking into a room where the lights are turned to full brightness for the first minute, then dimmed for the rest of the night. If you only glance in that first minute, you might conclude the room is always that bright. Some early galaxies may be like that, caught in a brief blaze that exaggerates their apparent, grown-up nature. But there is another layer to this story that feels almost like listening to the universe breathe, and it begins long before any galaxy shines. After the Big Bang, the cosmos was a hot plasma where light could not travel freely. Then came recombination, when electrons and protons joined to form neutral hydrogen, letting photons finally stream outward. Those photons are still here, stretched by expansion into the cosmic microwave background, the oldest light we can see, a faint afterglow that carries a portrait of the universe as it was when it first became transparent. That afterglow is not just a relic. It is a ruler, a memory, a baseline against which every later structure must make sense. If early galaxies appear too massive too soon, we naturally ask whether we have misread the later chapters, or whether we need to reread the prologue written into the CMB. Because the CMB tells us the starting conditions, how smooth the universe was, how large the initial ripples were, how matter and energy were distributed. Those tiny variations are the seeds of everything. If the seeds are slightly different than we think, the forest could grow in a different pattern. And this is where the mystery becomes both scientific and quietly poetic. The oldest light, nearly uniform, whispers that the universe began with near perfection. Yet the galaxies we see later suggest a hurry, a rush toward complexity. Somewhere between those two truths lies a missing nuance, not a contradiction, but a refinement waiting to be understood. So we circle back to mass estimates. Could we be overestimating the stellar mass because we are assuming the wrong kind of stars, the wrong ages, the wrong dust properties? Could we be mistaking the glow of an accreting black hole for the combined light of countless suns? Could gravitational lensing be quietly amplifying some of these sources, making them appear intrinsically brighter than they are? These are not excuses. They are responsible questions, because the universe is not obligated to be puzzling. Sometimes our measurements are the puzzle. To make this more tangible, consider a second image. Picture two fireplaces behind a curtain. One is a large fire burning steadily. The other is a smaller fire fed by a sudden gust, flaring bright for a moment. If you only judge by the glow on the curtain, you might swear the smaller fire is the larger one. Now translate that to the early cosmos. A compact galaxy in a short, intense star-forming phase can throw an outsized glow across billions of light years, especially when the light is shifted into wavelengths our instruments are designed to catch. And yet, even with every caution, there remains the most provocative question, the one we hesitate to say out loud. Could the timeline itself need a subtle adjustment? Not in a way that discards everything, but in a way that acknowledges how much depends on our cosmic clock. If our inferred expansion history at very early times is slightly off, or if certain parameters behave differently in the young universe, then the conversion from redshift to age could shift, giving gravity a little more time than we thought. This is delicate terrain, and the field treats it with care, because changing the clock touches nearly every inference we make. But as Stephen Hawking put it, the greatest enemy of knowledge is not ignorance. It is the illusion of knowledge. When observations refuse to sit comfortably inside our expectations, the most honest response is not panic, but attention. What makes this moment special is that it is not a collapse of understanding. It is the feeling of a map becoming sharper. The early universe was not a quiet nursery. It was a place where small differences mattered immensely, where the faintest imbalance could grow into a galaxy, where darkness was not emptiness but potential, and where the oldest light still hangs in the sky like a memory you can almost touch. If the first galaxies truly formed faster, shone brighter, and organized sooner than we predicted, then we are witnessing the universe reveal a deeper efficiency, a more elegant impatience, a talent for structure that our simplified stories have not fully captured. And maybe that is the most educational gift of all. Not that science always has an answer ready, but that it knows how to listen when the cosmos speaks back. Because every time we trace these distant lights, we are not only looking outward, we are learning how origins work, how complexity appears, how a nearly uniform dawn became a sky filled with islands of fire. What if the very first stars were never meant to be seen, only inferred, like footprints on a shore after the tide has gone? We call them Population 3, but the name feels almost too clean for something so wild and unfamiliar. In our best stories and simulations, they are giants, born from nearly pure hydrogen and helium, with no heavier elements to help the gas cool gently. That changes everything. When gas cannot shed heat easily, it collapses in fewer, larger clumps, and the stars that ignite can become monstrously massive, dazzlingly hot, and heartbreakingly brief. They would burn like white furnaces, pouring out ultraviolet light strong enough to bruise the surrounding darkness, and then vanish in a blink of cosmic time, ending as titanic supernovae or collapsing into black holes that become the seeds of later monsters. And that is exactly why we have not photographed one in the act. They lived fast and died young, they formed in the most remote eras, and their light is stretched by the expansion of space until it slides into wavelengths that are hard to catch. Even worse, the fog between us and them was not yet fully cleared. Neutral hydrogen loves to swallow ultraviolet photons, so the early universe was not only far away, it was also partially opaque to the very kind of light these stars would scream into existence. A useful way to picture the challenge is to imagine trying to identify the very first match ever struck in human history by staring at a modern city from the other side of an ocean. The glare of countless streetlights would drown it out, and the air itself would blur the view. Population 3 stars are like that match. We do not miss them because our instruments are weak alone. We miss them because the universe quickly surrounded their memory with brighter, messier descendants, and because the medium they illuminated was still learning how to become transparent. That brings us to reionization, the slow turning of the cosmic fog into clear air. After the cosmic microwave background was released, the universe cooled enough for electrons and protons to pair up, forming neutral atoms, and light finally traveled freely. But freedom did not mean brightness. The universe entered a long, quiet interval where no stars yet shone, and then, gradually, the first sources of ultraviolet radiation began to tear electrons loose again, reionizing hydrogen and transforming the intergalactic medium into a thin, hot plasma. Here the question is not only what happened, but how quickly it happened. Did the universe flick on like a lamp? Or did it brighten like dawn, uneven and patient, with pockets of light widening over hundreds of millions of years? The most honest answer is that the evidence points to a drawn-out process, but with room for surprises. We can read reionization indirectly through the way early galaxies appear or disappear at certain wavelengths, through the imprint on the background radiation, and through the emerging promise of mapping neutral hydrogen via its faint radio signature. Yet each method is like listening to a symphony from outside the concert hall. You hear the shape of the music, but you debate the tempo. Some interpretations suggest the dawn rose earlier or more efficiently than older models expected, while other results remind us that measurement is delicate when the signal is thin and the noise is loud. And in that uncertainty, the story becomes more interesting rather than less. Because once you ask about reionization, you are forced to ask who the main character really was in the cosmic dawn. Was it those first massive stars? The purest flames the universe ever lit? Was it the first galaxies, not just single beacons but whole neighborhoods of star formation, combining their light into expanding bubbles of ionization? Or was it the early black holes, feeding and flaring as quasars, releasing high-energy radiation that could carve through vast regions of gas? The universe likely used all of them, like an orchestra that cannot be reduced to one instrument. But it matters which section carried the melody, because the answer tells us how structure formed, how quickly complexity emerged, and how the first environments suitable for later chemistry were prepared. This is where the cosmic microwave background quietly re-enters the conversation, not as a historical footnote, but as a guidebook. The CMB is the universe's earliest photograph, but it is also a map of tiny density variations, faint ripples in a newborn sea. Those ripples are the reason anything happened at all. Without them, matter would have remained spread evenly, gravity would have had nothing to grip, and no star would ever have found a birthplace. It is humbling to realize that the grandest structures we know, galaxies, clusters, filaments, may trace back to differences so small they are almost an insult to our intuition. As Stephen Hawking put it, we are just an advanced breed of monkeys on a minor planet of a very average star. And yet, in the same breath, that perspective makes our ability to read the CMB feel like a miracle of comprehension. Now, when modern telescopes show galaxies appearing surprisingly early, surprisingly bright, the natural temptation is to say the young universe matured too fast. But too fast is always relative to the model you expected. If early stars were more massive on average, their light would be intense and their feedback violent, changing how quickly gas fragments and collapses. If star formation in early galaxies was more efficient, those systems could build up stellar mass quickly. If dust, nebula emission, or active black holes contribute to the brightness, we might overestimate how many stars are truly there. Or perhaps gravity gathered matter faster in some regions, because the scaffolding of dark matter was arranged in ways our simplified pictures do not fully capture. An everyday analogy helps here. Sometimes a child seems to grow overnight, but what you are really seeing is a change in posture, confidence, or context, not a violation of biology. Likewise, an early galaxy can look mature because of how it shines, not only because of how much mass it holds. Still, it is fair to ask whether the standard cosmological model is missing something. Not in the sense that everything is wrong, but in the way a beautiful map can omit a few roads that matter in the hills. Perhaps the behavior of dark matter on small scales is subtler than we assume. Perhaps early feedback processes are stronger or weaker than our prescriptions. Perhaps there are unknown astrophysical populations contributing to ionizing photons. In science, missing pieces often announce themselves not with explosions, but with gentle mismatches that refuse to go away. As Carl Sagan reminded us, somewhere, something incredible is waiting to be known. The early universe is exactly that somewhere. Not because it contradicts everything, but because it asks us to refine the story with more patience and better listening. And then there is the Big Bang itself. Is it a precise moment, a clean timestamp, an instant labeled 0? Or is it a boundary in our knowledge, a horizon where our equations still speak confidently but our understanding becomes more like a fog than a clock? In practice, we use Big Bang as a powerful summary. Expansion, cooling, the formation of light elements, the release of the CMB, the growth of structure. But the closer we try to push toward the first instance, the more our known physics strains. We can describe the universe back to extraordinary early times, yet there remains a point where the language of our theories no longer fits smoothly. And that is not weakness. It is honesty. A second example may help you feel this. Imagine reading a book that begins mid-sentence and then trying to reconstruct the missing first page from the rest of the chapters. You can infer a lot. You can narrow down possibilities. You might even be mostly right, but the very beginning still feels like a torn edge. So when we wonder what population 3 stars looked like, we are also wondering what kind of universe could give birth to them. When we debate how fast reionization proceeded, we are asking how quickly darkness learned to become transparent. When we argue over the main character of the cosmic dawn, we are really asking what kind of engine the cosmos preferred at its first awakening. And when we confront the possibility that the early universe matured faster than expected, we are not watching science crumble. We are watching it do what it has always done: return to the evidence, adjust the rhythm, and keep walking forward without pretending the path is finished. In the next part, we will step back to the first light we can truly see, the cosmic microwave background, and follow its faint ripples into the long night that came after, until the earliest sparks finally learned how to hold. Was the cosmic dawn merely a physical transition, or was it the moment the universe began to see itself for the first time? In the language of equations, it is described as reionization, the ignition of the first stars, the lifting of a primordial fog. Yet behind those technical terms lies something deeper. For hundreds of millions of years, the universe existed without eyes, without beacons, without memory. Matter moved, gravity worked patiently, but nothing shone long enough to leave a lasting trace. When the first stars ignited, the universe did more than produce light. It created contrast, structure, and history. Light made distance meaningful, time readable, and space observable. In that sense, the cosmic dawn was not only an event, it was the birth of awareness at a cosmic scale. Darkness always comes first, not because light is weak, but because light requires preparation. In the universe, darkness allowed matter to cool, to settle, to gather quietly under gravity's guidance. Only then could light emerge and persist. Human understanding follows the same rhythm. Confusion, uncertainty, and silence often precede insight. We do not learn in flashes alone. We learn because we sit with not knowing long enough for clarity to form. The universe teaches this lesson without words. And when we observe ancient light today, stretched and softened by billions of years of expansion, the question of who is observing whom becomes unavoidable. We think we are studying the universe, decoding its past with instruments and models. But in truth, that light is also shaping us. It enters our detectors, our minds, our stories. The atoms in our bodies were forged in stars that came after that first dawn. Our curiosity itself is a consequence of cosmic illumination. So the cosmic dawn is both a physical threshold and a symbolic one. It marks the moment the universe became visible, structured, and narratable. In tracing it, we are not only reconstructing the origin of stars and galaxies, we are recognizing that consciousness, curiosity, and wonder are not accidents standing apart from the cosmos. They are continuations of its first light.